Welcome back to Algorithmic Game Theory. Today we are talking about another problem of mechanism design without money, which is about fair division. What are these fair division problems without money? You'll see them very often in real life. For example, you might consider a group of employees who have to decide which work shifts two of them works in. And some might say, okay, I rather work in the morning. Some others may say, okay, I rather work in the afternoon. Some might say, oh, I definitely want to keep my weekends free. Others would say, no, I'd rather work on the weekend than during the night. And just everybody will have their personal preferences. How do you get to an assignment that makes everybody as happy as possible overall? We'll be considering this in a very simplified setting. So you could, of course, consider this with, for example, indivisible items. You know, we've seen indivisible items a couple of times this semester, but we'll now consider a fully divisible resource. But the thing is, people prefer different parts of that resource. And what does this resource usually look like? Well, what people usually are considering is the problem of cake cutting. So this is the kind of cake you should have in mind. It is just a linear cake, and then you may just cut it into pieces, and people will prefer different parts of the cake. Some people might prefer, for example, this white chocolate part. Some people may just prefer the plain black chocolate part, or somebody might prefer the sprinkles, depending on what you personally prefer, depending on your personal taste. So how do we capture such a setting mathematically? So this might be our cake. And how do we model this cake? We'll model it just as an interval going from 0 to 1. So this will be just the interval 0 to 1. And we can cut this into pieces. And what is a piece? A piece is just a union of subintervals. We'll have n agents, and each agent I has again a valuation function, which now assigns a non-negative value to each piece of the cake. We'll assume to capture this. So this valuation function, this is called capital VI. And we'll assume that there is a density function small vi, which maps from 0, 1 to the non-negative reals, such that capital Vi of x is given as the integral over all x in x, this small vi of x. So in particular, if we're assigning you the interval from A to B, then your value for that will be just the integral from A to B of this small function vi. So just integrating over this density. And if X is a disjoint union of intervals, then the value will be just the sum of these two integrals. In other words, this valuation function is additive across different intervals. Disjoint intervals, I mean by this. One thing to notice at this point is that it doesn't actually matter whether we assign open or closed intervals, just because the integral from A to A, for example, is 0. So getting this, what does this even mean in the sense of a cake, that you have a cut at A and then you have another cut at A and you get everything in between? Well, that's nothing. So this is why we can safely assume that sometimes these intervals will be open, sometimes these will be closed. So that's actually not the point that matters here. We'll also assume that everybody values the entire cake the same way, but what matters is which part of the cake they prefer most. So do they rather prefer the white chocolate part or the sprinkles part, or which part do they prefer? So we'll also assume that capital Vi of the interval from 0 to 1, this is of course again the integral of this small vi, this density function, that this will be simply 1. So what might this now look like in concrete numbers? We might have somebody who just doesn't care which part of the cake they're getting. So then this density function would just be 1 everywhere. Or we might have somebody who says, okay, I definitely prefer the first half because there my density is maybe like 3 halves. And in the second half, the density is only 1 half. So they, for example, again value the entire cake as 1, but the first half of the cake so what this guy now says is just half of the cake. This guy here says, okay, that's actually, well, a quarter versus 3/4 of the cake. So that's just the difference of personal perception. How much do you value which part of the cake? So what could we do here? For example, we could choose as an allocation we could set that the first agent is getting the first half and the second agent is getting the second half. So this, we want to make sure that these are disjoint intervals so that no part of the cake is allocated twice, but as I was saying, we don't care whether these are open or closed intervals. So from the perspective of agent 1, this looks like a very fair division. Why that? Because agent 1 now sees, okay, my value for what I'm getting is just the same as for what the other is getting. This is, in both cases, a half. But what does the second agent say? Well, the second agent now says, this is pretty unfair, because I am getting only a quarter of the cake, whereas you are getting 3/4 of the cake. And what you realize is if we now switch the two, if we swapped the allocation of A and B, then agent 1 would still not care. For agent 1, this would be a fair allocation either way, but agent 2 would care. Agent 2 would suddenly be super happy because from their perspective, they are suddenly getting 3/4 of the cake, as opposed to the other agent getting only 1/4 of the cake. So what we should discuss is how can we model fairness here? Why, or what is it that makes an allocation fair? And is there always a fair allocation? How can we find it? What is a fair allocation? Well, that's not easy to define because every agent has their own perspective of what is a good part of the cake that we're cutting. So there is just no outside perspective of saying, okay, you now get half of the cake, you get half of the cake, because there is just always this personal perception of what actually corresponds to half of the cake. And indeed, this is why there are multiple different fairness properties. Let's see 3 of them. So once again, our goal is to find an allocation, capital A, consisting of A1 through AN, where these AI are disjoint and the union of them is the entire interval. And of course, all of them are subsets of 0, 1. And this allocation should, of course, be fair. But what does this mean, this fairness? Well, we could, for example, say it should be proportional. What does proportionality mean? It means that every agent thinks that they are getting at least a 1/n fraction of the cake. There's also the notion of envy freeness. Which means that for all I and j, for any 2 different agents, agent I is happier with what they are getting, or at least as happy as with what they are getting, as if they were getting what agent J is getting. Or there's a third property, namely, this is equitability. Which means that every agent thinks that everybody is getting the same. So that for any I and any j, the value for I that agent I has for the set AI should be equal to the value that they have for what anybody else is getting. So you see, this is something that is stronger than this second property, because it is just equality, where here we just have inequality. And proportionality, that's still weaker than envy freeness, because if this does not hold, then, or let me say, if envy freeness holds, then you definitely think that you're getting a 1 over n fraction of the cake, because everybody else, from your perspective, shouldn't be getting more than 1 over n fraction. There are n agents in total, so n minus 1 other agents, and if any of them got more than what you think is a 1 over n fraction, and you got less, then this would also give you envy. So as you see, these are proportionality is the weakest of all, envy freeness is a little stronger, and the strongest of these is equitability. Is there always an allocation that is proportional? How would we find it? And how often would we have to cut the cake? How would a protocol for this look like? The first protocol that I'd like to consider is just for 2 agents. And this is the famous so-called cut and choose protocol. This is, I guess, a protocol that many of you know. At least if you have siblings, you probably know this. You just want to divide one divisible good among just 2 agents. And how do you do this? One of the agents cuts it, and the other then chooses what they're getting. And why is this perceived a good way of allocating things? Because the first agent will just try to cut things as evenly as possible so that they are actually happy with whatever they are getting. So formally, agent 1 cuts at point T such that the value for the first part is exactly equal to the value for the second part, from their perspective, so from agent 1's perspective. And this will of course be a half because the entire interval is valued as 1. Then agent 2 chooses between 0 to t and t to 1. Which of the properties does this allocation fulfill? Recall that we were asking about proportionality, that we were asking about envy freeness and about equitability. Is this proportional? Let's see. This allocation is proportional. Why that? What did this mean to begin with? We would now need that every agent values what they're getting by at least a half. Why is this true for agent 1? For agent 1, we'll have that agent 1 actually does not care which of the two pieces they're getting. They value both of them at 1. And for agent 2, what do we have there? There, of course, we have that they are choosing, so the value for this piece has to be at least the value that they have for that other piece. And as you see here, in this argument, you also see this will be an envy-free allocation because agent 1 actually sees, okay, I don't envy agent 2. Same is true for agent 2. So both agents are happy with what they're getting and they don't envy the other agent. But will this allocation be equitable? What did this mean? This meant that every agent values what they're getting exactly the same. So once again, each agent values everything that anybody gets exactly the same. And this allocation will not be equitable. Namely, we could have, for example, that the first agent has a value of, or a density of 1 everywhere, and the second agent, they now have a density of 2 in the first half, and a density of 0 in the second half. What would the first agent do? The first agent would cut at exactly a half, because this makes it feel that both parts are valuable exactly the same. And then the second agent will choose the first of these two halves. And what are the different values? The different values are a half for the first agent for both of these, like we always have. This is generally a property, but the second agent now has a value of 1, a value of 0 for what the other agent is getting, and a value of 1 for what they are getting. But there is actually an equitable allocation. Namely, we could set a 1 to the interval of 1/4 to 3/4, and a 2 to what is left. So we'll take the interval from 0 to 1, take away a1. This, of course, is not one piece as we might understand it. This is not a contiguous interval, what agent 2 is now getting. But you can now figure out that for agent 1, this is exactly has value a half. For agent 2, this here also has value exactly a half. And the same is true for that other interval, just because overall it has to have a value of 1. So in this case, there is no contiguous equitable allocation, but there is an equitable allocation. And now, speaking of cut and choose, there's one more thing I'd like to remark, namely, if we go back to this protocol, then you'll see, okay, this will not be incentive compatible in a way that you will actually, that you cannot gain from strategic behavior. So all that we're talking about today is just what can a fair allocation look like. We are not talking about these strategic aspects that you might be strategically misreporting because this will make you better off. Because this could happen here. We say that agent 1 cuts the cake into 2 pieces, and we are now saying, okay, they just cut the cake so that they don't care which of the 2 halves they're getting. But this does not mean that there is no smarter way for them to cut the cake. For example, it might be, in this case here, if you were now acting strategically, what would you do? You, of course, as agent 1, wouldn't cut the cake at a half, but you would say, okay, maybe now I cut it at, say, 1/3 or so. Because then I know, even then, agent 2 will take this from 0 to 1/3, and I'll get everything from 1/3 to 1. So I'll get way more. And this is something that you might consider, so strategically cutting your cake so that you anticipate what other people will be taking so that actually you are best off. But this is not the point today. The point is just, given that we know these values, how can we find an allocation that makes people happy? How do we define happiness? We've seen 3 different properties. And is it always possible to find such an allocation? How difficult is it to find that? And indeed, for envy freeness, for just 2 players, 2 agents, it is easy to find such an envy-free allocation. For coming to an equitable allocation, this seems to be a little more difficult. Now what we want to do next is we'll talk just about proportionality, which was the easiest of these properties, and then we'll see how we can actually guarantee this even for any number of agents. Now we want to see how we can get a proportional allocation for any number of agents. Recall that a proportional allocation is defined in a way that every agent thinks they are getting at least a 1 over n fraction of the cake. How can we do this? We'll actually do this in a very similar way as cut and choose, but now all of our agents propose one place where to make the first cut, so that what's left of that cut is at least a 1 over n fraction. And then we take the leftmost of these cuts, and whoever said, okay, this would be enough for me, is getting this, and then we recurse with the remainder of this cake. So more formally, we initialize T0 as 0 and N1 as n. And now for k going from 1 to n minus 1, we'll do the following. For every agent that is in nk, let tki be the point such that, taken from tk minus 1 to tki, we'll see a value of exactly 1 over n. Where this notation that I'm now starting to use here means I'm now writing v of a comma b just for the vi of a comma b for just the value of the interval from a to b. So we have already cut the cake up to tk minus 1. So only what's from tk minus 1 to 1, this is only what is left of the cake. And then we're asking, okay, where now how much would you need to get this 1 over n fraction? And now we let I star be the agent with the smallest tki, and we let tk be equal to tki star, and ai star will be the interval from tk minus 1 through tk. And then we'll set nk plus 1 to nk take away I star. And then everybody except for the remaining agent is getting something, because this way we're assigning only something to n minus 1 agents, and then we will assign the remainder to the remaining agent in n. So one other way You can think about this as a moving knife protocol. So what will happen is that there is a knife moving over the cake, and then people scream stop, and whoever screams stop, whoever is the first to scream stop, then gets the fraction of the cake that is left of that knife. However, as you see, this more feels like a first price auction. So once again, this is not incentivizing agents to report their true values. This is not our question today. But nonetheless, we can show that this always gives us a proportional allocation. How do we show that? We claim that the allocation computed by the algorithm fulfills proportionality. And to see why we have a proportional allocation, we should have a look back at this algorithm. And the thing that we should be asking is this even a feasible allocation? Is this even a feasible algorithm? Is this even well defined? Is there even such a point TKI such that you value what is left by exactly 1 over n? Or could it be that you value everything from tk minus 1 up to 1? So all that is remaining of the cake that is still not allocated, that you value all of this less than 1 over n. Could that happen? Or also, what about the remaining agent? Will they value what they're getting at least 1 over n or not? And indeed, it is not difficult to show that none of this will happen, because as an invariant, we'll have that everybody who is still in the set nk at every point in time values what is left of the cake, so what has not been allocated of the cake, they value at least 1 over n. And this makes sure that this is not happening down here, that whatever the remaining agent is getting, that they're happy with this. And also that the agent, that everybody can actually say some point TKI for which this is true. And of course, then what they are actually getting, this will definitely have a value of 1 over n just by definition. So more precisely, we'll show the following invariant, and I think I stated this a little incorrectly before. For any k and any I in nk, we'll have that the value that buyer I, sorry, not buyer, agent I, we should say today, because they are not buying, and they're not bidding, and they're not playing, they're just some agents who want to get something, and that this will be at least 1 n minus k plus 1 over n. This in particular makes sure that for k being equal to n, the last agent remaining will be happy, and also in between everybody can say, okay, this much of the remainder gives me a 1 over n value. How do we show such an invariant? We show it by induction. Namely, we'll have the case that k is equal to 1, then we'll have that vi of 0 to 1 will have to be at least 1. This is by definition. Because we say, okay, they value the entire cake by 1. Now let's consider some k plus 1, which will be greater than 1. What do we have? We'll have that for every agent in the remaining set nk plus 1, tki will be at least tk. Because tk was the smallest such value. This now means that vi of tk minus 1, comma tk will be at most vi of tk minus 1, comma tk, comma I, and this, we said, is exactly 1 over n. And now, by induction hypothesis, agent i's value for the remainder from tk to 1, this will be, because we're still additive, the value for what we have from tk minus 1 to 1 minus the value that we would have from tk minus 1 to tk. Now for this, we know that this is at most 1 over n. For this part, we know that it is at least n minus k plus 1 over n. So what we're getting in total is that this is at least n minus k plus 1 divided by n. And this completes the induction. So once again, how did this argument work? We just said, okay, what is remaining of the cake at any point in time? Every of the remaining agents values high enough, namely every of the remaining agents says that we can cut it into pieces so that, from my point of view, every of the agents will get a 1 over n fraction. And because we can do this in every step, this is a well-defined algorithm in the sense that there is always this point for which I myself am getting a 1 over n fraction, and also that this remainder is also has a certain value to this agent, whoever is getting this. However, you can see that this is not NV-free. Why isn't this NV-free? Because you might be the first agent who's getting something, and then you think, okay, I'm not getting a 1 over n fraction, so maybe it's like 3 agents. I'm getting a third of the cake. And then you suddenly see, okay, actually, these other 2 agents, they have weird preferences. So for example, then there is somebody who's taking, from my perspective, only like a tenth of the cake. And then most of the remainder is actually going to one agent, which was, so 2/3 minus a tenth, for example, is then going to only one agent. So I will certainly envy this agent. So it's not envy-free, but at least it is proportional. Getting envy-free allocations, this is much more complicated. And indeed, for n agents, this is, at least for now, hopeless to describe, although it has been shown that it is possible. But what I'd like to do next is to show you how we can achieve this for 3 agents, how we can achieve envy-freeness for 3 agents. Now we'll come to the question how to determine an envy-free allocation if we have 3 agents. And even this is surprisingly complicated. Maybe so far you've thought, okay, this is actually super easy. Why do people care about this? And indeed, this proportionality, this is indeed extremely easy, but then now you see this envy-freeness, which sounds much more desirable, that I don't envy anybody. This is far more complicated. And indeed, we'll now show a protocol which cuts the cake into pieces so that every agent gets some parts of the cake, but no agent envies any of the other agents. And the amazing thing is, we only will need 5 cuts, which means we'll get 6 intervals. So it's not like you might be hoping, okay, cut here, cut there, and then you get this, you get this, you get this. But it is already much more complicated. And when we're showing why this will be envy-free, you'll hopefully get an idea why you can't do this in a much easier way. This, by the way, is an algorithm with an interesting history because it was invented independently by John Selfridge and John Horton Conway, but unfortunately none of them ever published it. So maybe if you find out something, you should rather publish it so that you actually get credit for it and not somebody else finds out the exact same thing. How does this work? Well, we'll start as follows. Agent 1 cuts the cake into 3 pieces x1, x2, x3, such that agent 1 has the same value for each of them. Now we will rename them so that agent 2, whose values are of course a lot different, or might be a lot different, otherwise it gets only easier, is that agent 2 actually of these three prefers the first to the second to the third. Where are we so far? So there are three pieces of our cake. Agent 2 says I like the first piece best, the second piece I like less, and the third piece I like least. Agent 1 says, okay, I don't actually care, I like all of them the same way. Now, agent 2 cuts off a part of the first piece such that the first two pieces are actually have the same value for them. Things would be much easier if we were allowed to just discard what we're cutting off, but we aren't. And this is what makes things very complicated soon. So, what's the current status? Agent 1 says now, yeah, x1 take away x prime, I don't know, that's maybe doesn't make me happy. That's the other two make me happier. The other two, I don't care which of the two I'm getting. X1 take away x prime, I'm not so happy with. Agent 2 says, okay, I don't like the third piece, but I like this trimmed first piece, and the second piece I like the same. And so let's now ask agent 3 what they actually prefer out of these three things that we have now. This trimmed first piece, the second piece, the third piece. So this will be our first assignment phase. Where we will be assigning 0, 1, take away x prime. X prime, this was what agent 2 cut off. What will happen now? Agent 3 chooses one of x1 take away x prime, x2, and x3. And if agent 3 chose x2 or x3, then agent 2 gets x1 take away x prime. Otherwise, they get x2. And agent 1 gets x2 or x3, depending on what is left. So what is happening so far? We had these three pieces, x1 take away x prime, x2, and x3. Now we let agent 3 choose one of these three. Agent 3 will of course choose the one he likes most. And then agent 2 gets either x1 take away x prime or x2. Why that? This is what agent 2 values the same, and there is also this set x3 which agent 2 values only less, definitely not more. And then there's agent 1 who gets whatever is left, and the amazing thing is they get x2 or x3, but they don't actually care. So what is now great about this is that agents 2 and 3, so 2 and 1, they will definitely be regardless of what of the two options they're getting that we're writing here, they have the exact same value for these. But there is something that is complicated about this. Namely, there's still this x prime left that we still have to allocate. And for this, we'll now have a second assignment phase. So this will be the second assignment phase. In which we're assigning x prime. And to write this, let capital T be the agent who got x1 take away x in the first round, and T bar we let them be the other one. Quite importantly, agent 1 is never the one who's getting x1 take away x prime, because this is either taken by agent 3 or by agent 2. Now we'll have to also assign x prime. How do we do that? Agent T cuts x prime into x1 prime, x2 prime, and x3 prime, such that, so that's not agent T, that's agent T bar, such that they value both all of these three the same. Then agent T chooses one of the three. Then agent 1 chooses one of the remaining two. And then agent T bar gets the remaining piece. And what we now claim is that this allocation is NV free. Whew. How do we show this? Well, all we have to do is we'll have to verify the envy-freeness inequalities. What were these envy-freeness inequalities? Agent 1 should not envy Agent 2, and Agent 1 should not be envying Agent 3, and so on. So we'll have in total 6 envy-freeness inequality, all of which we'll have to verify. We'll first say that without loss of generality, in the second phase, T chooses x1 prime and 1 chooses x2 prime, and T bar then gets as the remainder this x3 prime. Where was this happening? This was this last phase. Here we said, okay, agent T bar cuts this into 3 pieces, which so far just we said have all the same value, but we now say, okay, agent T will actually choose this one, agent 1 will choose this one, and agent T bar will choose this one. This is just to simplify our notation here. So why is it that envy-freeness is fulfilled? Let's first consider agent T. What is it that agent T is getting? Agent T is getting x1 take away x prime. This is how agent T was defined. We let agent, so here in the first phase there was somebody takes x1 take away x prime, and then we call T the one who got this, and then they also got x1 prime. So they're getting x1 take away x prime union x1 prime. What will we now have? We will always have that the value for this is at least the value for the set x2, so the value for x1 take away x prime, and this is also at least the value for x3. This is something I argued before because this is something that we can see happening here. Whoever gets x1 take away x prime, they are actually happy with that compared to getting x2 or x3. Good. Now what else do we have? Here now, out of these 3, agent T is the first one to choose. So we'll also have that the value for x1 prime is at least the value for x2 prime, and the value for x1 prime is at least the value for x3 prime. And if you now look at this, you'd see, okay, regardless of how you combine this, whether you now combine x1 prime, x2 with x2 prime, or with x3 prime, or if you combine x3 with x2 prime, or x3 with x3 prime, agent T will always be happier with x1 take away x prime union x1 prime. Good. This was agent T, which was one of agents 2 and 3. The other one we called agent T bar. So let's now consider agent T bar. Now we'll have to again argue that they're actually happy with what they're getting in the first phase. So let's just shorten this here. In the first phase, agent T bar gets the most valuable of the pieces, and in the second phase, agent T bar cuts the pieces so that they have the same value. So certainly we won't have envy here, because if you get the most valuable of the pieces in the first phase and then in the second phase you were the one to cut the pieces, this means that you won't envy anybody, because they are getting only less valuable pieces in the first phase and only pieces that are as valuable as yours in the second phase. Now let's consider agent 1. We'll now have to talk about why don't they envy agent T and why don't they envy agent T bar. And maybe let's go back. Agent 1 was the one who cut the pieces into equal size in the first, at the very beginning. And then somebody cuts off something of this piece x1, and then maybe this or maybe the other agent, so either agent 2 or 3, they are taking away this x1 take away x prime. And so regardless of whether agent 1 now gets x2 or x3, they certainly won't envy the agent who's getting x1 take away x prime plus something else. So agent T gets only a subset of x1 Well, agent 1 actually originally cut the pieces so that they are all the same. So this means that agent 1 will not envy agent T. Importantly, because agent 1 is getting either x2 or x3. Now what about agent T bar? For this we'll have to look at the second round, the second assignment phase, and there actually agent 1 chooses before agent T bar. So agent T bar actually, or agent 1 prefers what they're getting to what this other agent is getting. So we'll have that agent 1 has a value for x2 prime of at least a value for x3 prime. And agent T bar gets x2 or x3 plus x3. And so what we also had was that they were cut to the same size by agent 1. And if you now see this together, then agent 1 will not envy agent T bar. Good. So having another look at this protocol, you see it is indeed complicated. And for me, it was most enlightening when I tried to write this down and I wanted to simplify this, when I wanted to say, okay, why do I actually do this stuff? And then I realized, okay, I will have to do this because otherwise agents will envy each other. And because I cannot just discard something. And this is what I meant earlier when I said, okay, if we didn't have this to allocate this x prime, things would be much easier, because then we would be done after the first assignment phase. We would have one agent cutting the cake into 3 pieces, another agent cutting off something, throwing it out, and then the third agent chooses one of these, and then the other 2 agents can be made happy because they chose to cut the cake so that that they, to some extent, don't care. But the difficulty is that we have to actually allocate everything, and this is why we are then going through this second assignment phase, in which we're doing the same thing again, meaning that again we'll cut. Somebody cuts the cake into pieces, then somebody chooses, and then somebody else chooses, and only then the one who actually cut the cake or the remainder of the cake then again gets something. And this is the general principle that you have to follow. Indeed, it has been an open research question of whether something like this can always be done, and it has been answered affirmatively some years ago. Namely, what was the question? The question was, can we at least bound the number of cuts? So here we have in total 5 cuts. There's 5 times something cut of the cake. Can we bound this in terms of n, the number of agents? Because so far, everything that had been known was things that where the number of cuts actually depends on the on the valuations. This is something that you can do here, of course, as well, that you probably just cut the cake into infinitesimal parts and then you rearrange it so that everybody gets happy. Everybody gets the same amount, but how can you now ensure that you're doing this with only finitely many cuts, or this even with a number of cuts that is bounded only in n and does not depend on the valuations? This is much more complicated. And as you see, well, even for three agents, it all is difficult, and it certainly doesn't get any easier if you have more than 3 agents. And of course, there's still the open question of what happens under misreporting, if agents can actually misreport or choose cuts strategically so that they actually gain something because they know that other agents will be choosing something. I'm not aware of any research on that. I guess this would be also in the context of this entire lecture, this would be something very interesting, but I'm not aware of any ongoing research on that. Good. So this concludes our lecture for today. In usual times, you would now be able to eat the cake, but those aren't usual times. So stay safe. See you next time. Bye.